I need to.
Yes. Pull it. Yeah.
So, as a dean, I was very pleased to see that you had a very productive and interesting talks during the last 3 days. And as a dean, I was very pleased to see that some of them were delivered by our graduates. I mean, the brilliant researcher, academician Mia Kagarka, a well-known specialist in alkaline magnetism. Yesterday, we heard another talk given by another our graduate, Professor Artyom Aganov. It was devoted to high-pressure mineralogy, and Artyom is very famous for his works connected with prediction of some phases which can be attributed with zone D2 strokes, such as post-perovskites, carbonates, and so on. This morning, you will hear the presentation by Professor Klitschov, Pavel Klitschov, famous for his works, for his studies of ancient and modern volcanic magnetism. And tomorrow, he was also another our graduate will give a talk. I mean, Professor Igor Pekov, who is a unique mineralogist, to discover about almost, more precisely, 193 new minerals, and this is absolute record during the scientific history. As I already mentioned, the organizers of our seminar asked me to say something, to describe briefly a few words about the geological department of Moscow State University. And I would like to recall that Moscow University was established 260 years ago by academician Mikhail Lomonosov. And geology, the lectures in geology were given from the very beginning from the first years of establishment of Moscow State University, because Lomonosov graduated from Freiberg Mining Academy, and Freiberg is a capital of classical geology, and thus, in this sense, we had some privilege. However, the geological department as a separate unit within the structure of Moscow State University was established 78 years ago. Well, the new epoch in our history, in the development of our department, is connected with the management of this building, which was constructed in 1953. And you can see that now geology department comprises 17 chairs, which cover all the branches of modern geology. Our staff includes 180 professors and teachers and 160 researchers. And we occupy, in this building, we occupy the floors from 3rd to 8th, and I can add the height, perhaps somebody don't know, but the height of this building is 250 meters. And however, of course, it's very impressive, it's really skyscraper. However, if you compare with some oil platforms in Mexican Gulf or in North Sea, it's only half of the height of these platforms. So, as I would like to also to show you the biggest classroom of our faculty. It's on the 6th floor, and you will see also that during these last years, during the 75 years of Moscow Geology Department of Moscow University, more than 1,500 geologists graduated from our department, and a great number of PhD and Doctor of Science already completed their works. Actually, we have 1,200 students and 130 PhD students. So our faculty is rather big. Apart from the size, I want to say that our faculty is also has some specific features. And the first feature is connected with famous scientific school, which were organized and developed during the history of our faculty. I only mention 3 names which are close to highlights of our school. And number 1 is Professor Vernadsky, who was the head of the chair of mineralogy during more than 20 years. And who just worked here. Then Professor Academician Smirnov, who was the head of the chair of economic geology and ore deposits. He was vice president of Russian Academy. And Academician Belov, a former president of International Union of Crystallography, who was also in head of the chair of crystallography and crystal chemistry. And I was lucky to be his, student. And I always remember his statement that the scientist should live under the shadow of paradox. He wanted to say that by this statement that the scientist should be critical in respect to his own results, in respect to the results of his colleagues. In other words, according to George Bernard Shaw, to be devil's disciple. I think that this statement can be applied to any science. Well, and important, specific feature of our state of art at present time is that we develop academic exchange when professors from different universities come and to give their lecture courses, and at the same time our professors go to other universities. And here you may see that about a month ago, academician Dobritsov from Novosibirsk University gave a lecture course devoted to problems of geodynamics. At the same time, at the chair of oil and gas geology, they have a lot of, the specialists of this chair have a lot of contacts with industrial companies. And here you can see that the professor from well-known French oil company Total gave a lecture course. And here you can see the title of this course, Reservoir Drive Mechanism. So this is one specific feature of our university. Another specific feature is connected, and perhaps all of you agree, that the geologists, the education of geologists cannot be limited only by lectures or by seminars. So here you can see also that the theory behind the school desk is a practice, and practice in geological education plays a very important role. And we have several camps located in different parts of European part of Russia. And the ancient, the oldest camp is located in Crimea. And Crimea is not occasionally selected. The first practice in Crimea was organized in 1924. And I want to say that since 1938, there was no any interruption except the time of the war, but all generations of graduates of our department passed unforgettable time and passed unforgettable practice in Crimea, in mountain Crimea. So the Crimea is a unique place because its stratigraphy can be estimated by 300 million years. And different geological phenomena can be observed there. And I dare say that in 10 days, exactly, in June, 400 of our students will be transported by aircrafts to Crimea, and about 70 professors. The upper part of this slide reproduces the camp in 60th of last century, and the old generation of our graduates who are present here perhaps remember this, photo, recalls them the time they spent in Crimea. However, actually we reconstructed during last 15 years, and you can see the new cottages, student cottages, located in the photo on the lower part of this slide. This is the the future, avenue in this camp. Well, and as I said, different phenomena like weathering can be observed in Crimea, walk of sea, and so on. For me personally, it was an unforgettable time when we celebrated 50th anniversary of our camp. It was several years ago, and you can see that the students were very impressed. And then we had a concert organized by our students, and the spectator of this concert, the audience, were very satisfied. Well, and as I already mentioned, the third specific feature of our faculty is close contact with industrial companies. You can easily understand the necessity of such contacts because 60% of annual income in Russia is connected with mineral raw materials. And there are a lot of very important deposits of different minerals located within the Russia, and so we try to orient our students for the work of in different companies, in oil companies and oil and gas and so on. And we have a lot of contacts. Of course, this is here on this slide you can see the contacts established by our chair of oil and gas. They are among the companies which are our partners. You can see you can hear such well-known names like Statoil, like ExxonMobil, ConocoPhillips, Rosneft, Gazprom, and many others. And of course, every spring, the representatives of these companies come to our faculty and give presentations and recruit our students. For example, this is the presentation organized by ExxonMobil, but the former, this is the previous slide. Sorry, previous slide was organized by Russian company Rosneft, one of the biggest in the world. And this is ExxonMobil. So, a few words about social life and sports of our students. Perhaps, I address this statement to foreign guests. Perhaps you heard that the first Sunday of April we celebrate so-called geological festivity, and this is very, important event in the life of our students. In this year, to their dormitory came the rector, academician Viktor Sadovnichiy. So it was very, impressive festivity, and which is accompanied by traditional dinner. And sports. In the frame of Moscow University, there are actually 43 different faculties. They are of different size, small, bigger, and biggest, and so on. We belong to biggest faculty, and so this year we, in the sports competition within the structural units of Moscow State University, we occupy the third place, which is not bad in comparison with physics, mathematics, which are bigger faculties than our, and so on. So you can see, and we have very interesting persons among the students. For example, this lady, she is well-known alpinist. She graduates this year and receive master degree, and she obtained already the prize of World Alpinist, which is submitted to to ladies who just climbed on the mountains more than 6,000 meters. Her dream is to climb on Everest. Jamalungman. Well, and I would like to finish my short introduction with the slogan of Geological Congress: always win, but never be in a hurry. I think that on this basis, everybody can receive the victory in science and in life. Thank you very much for your kind attention. Now I pass, thank you. Now academician Ryabchikov, who is the chairman of this session, will announce and introduce the first speaker.
Thank you. Thank you, and after greetings by Professor Pushirovsky, let me open today's session. And the first presentation is by Professor Blundy from Bristol University, United Kingdom, Modern Methods in Igneous Petrology.
When do you want me to finish? 10 past 11. Okay. 40, it says, is it 50 or 40?
40 minutes.
Oh, it says 50 on there.
Really? But don't worry.
I'll just keep going till you've had enough of me. How about that?
Yeah.
Okay. All right. Okay, good morning. Thank you very much for inviting me. I apologise for the very bland title that this presentation has. It was done in a hurry. Obviously, it's modern methods in igneous petrology. I was going to lecture on old-fashioned methods in igneous petrology. That would be pointless. Do I have a pointer?
Pointer?
I can give. You'll press this one.
That one. Okay.
And,
Right.
Okay.
So, what I'd like to try and do today is just give you an overview of some of the work that we're doing in Bristol with collaborators around the world, trying to get an holistic view of crustal magnetism that integrates petrology and geochemistry and geophysics, and challenges some of the long-standing views about how crustal magnetism works. Yeah, maybe stick it this side.
Ярослав.
Надо, чтобы во весь экран.
Okay. Okay. My feeling is it was going well before we put that in.
Ярослав, надо помочь. Не получается, нет переключения.
Нет?
А где Ярослав?
Yep.
Он не может переключиться.
There we go. Okay. So, for a very long time, the view of magnet chambers was literally that a liquid-filled reservoir in which, in the words of the great petrologist Norman Bowen, the settling out from basic magma of certain minerals is the dominant control of the differentiation. So basically, we put large vats of liquid into the shallow crust, dense crystals drain out, light crystals and bubbles float, and that drives chemical differentiation, and it also fuels volcanism. I think it's increasingly clear, and I hope I can make a convincing case, that we need to move away from the magma chamber to something that I call a transcrustal magmatic mush, in which rather than having a discrete liquid entity at shallow level in the crust, we actually have melt distributed across almost the entire thickness of the crust, from the moho to the shallow crust, and rather than residing in a dominantly liquid state, it's in a dominantly mushy or partially molten state. And it's the movement of melt and gases through that mush that explains most of the igneous phenomena that we see today beneath volcanoes, and as I hope to show, in ore-forming deposits as well. So I'm going to try and convince you that we need to make the transition from here to thinking more in terms of the mush. And this is a paper we published 10 years ago, but roughly we fuel the system by basaltic, hydrous basaltic magma from the mantle, in the case of subduction zones, and that's the main focus here. Differentiation occurs within the, in this case, the deep crust, which would rise up to 10 or 15 kilometers, and differentiation involves crystallization, but also melting of the crust, and so we can produce magmas of both mantle and crustal origin. Why do we need transcrustal mush? What was wrong with the magma chamber? I think the thing that's become clear to me over the last 10 years or so is that as petrologists we should listen to geophysicists and vice versa. And the fact remains that our colleagues in geophysics can't find any magma chambers for us. They can't find large volumes of molten rock in the continents. There are skinny, thin axial magma chambers beneath the East Pacific Rise, but in continental settings, large volumes of liquid rock that cannot transmit S-waves are very, very elusive. And so we pretend, sort of in ignorance of each other, that these things exist, but geophysics tells us that they don't. We also know that many magmatic systems are extremely long-lived. We have very high resolution zircon dating that tells us that a magma system needs to reside for a very long time. And it's very hard to have long-lived systems at very shallow level because they're losing heat constantly through the roof. It's much easier to maintain long-lived systems at greater depth in the crust. And that's the second point. If we're going to do most of the differentiation at shallow level in the crust, we're going to have rather a lot of dense cumulate rocks, really at depths commensurate with the magma chamber, just a few kilometers or so. And on the basis of gravity alone, we just can't see very large positive Bouguer anomalies at shallow level in the crust. We also know that when we look at the chemistry of magmas that come out of volcanoes, they often show evidence of polybaric differentiation. That is, they've crystallized over a range of depths from the deep crust to the shallow crust, and that's hard to reconcile with a single body at shallow level. We have to melt the crust. There's lots of evidence for the involvement of crustal melts in continental magmatism. It's hard to melt large amounts of crust if you're doing assimilation at shallow level at the same time. And also, as I shall show at the end, and this really has some relevance to hydrothermal ore deposits, when we look at volcanoes, we often see a decoupling of when melt or magma is coming out and when gas is coming out. So I hope what I'll show you is an integration of petrology and geophysics. So here are some implications I hope we can go through this time. Architecture of subvolcanic systems, why volcanoes are the height they are, what the roots of volcanoes will look like. I'll show you some samples from the West Indies. What zone volcanic crystals can tell us about crustal magmatic systems, and if time permits, what we can learn about hydrothermal ore deposits. And I've put the collaborators for each of those projects there, and I hope you'll notice there's lots of Russian names there, so I feel this is an appropriate setting. Not all of those Russians live in Russia, though, I should point out. Okay, so TCMM, TCM, I made that up last night. A transcrustal magmatic mush. What's it look like? The best example in the world, by some distance, is one that underlies this region of the Altiplano. It's Chile, Argentina, Bolivia. This is the Altiplano, and there is a very large geophysical anomaly beneath the Altiplano at a depth of about 15 to 20 kilometers. That's called the Altiplano Cuna magma body. It's a geophysical anomaly because it has reduced S-wave velocities, and it's very conductive, and as I shall show, it actually has reduced density. It's not completely molten. It's partially molten. In fact, as I shall show you, it's around about 10 or 15% melt. It's huge. It's far and away the biggest the volume on there. It's about 500,000 cubic kilometers, and it ranges. It reaches from the west, the active margin, Andean margin of the west, some way into the eastern edge of the Altiplano. It underlies a series of volcanoes, and I'll show you this volcano here. U stands for Uturuncu, and its base is not very well defined, but the crust in this region, as you probably know, is the thickest anywhere in the world today, about 70 kilometers. And what lies above the APMB is something called the Altiplano Cuna Volcanic Complex, which is a series of volcanoes, most of which are dormant. There were some very large ignimbrite forming, I've lost my audience already, ignimbrite forming eruptions during the Miocene, but there's no active volcanism today in this region. Okay, so that is one of these deep crustal magma systems. Let's have a look at its surface expression. There is Cerro Uturuncu, a fabulous volcano rising 6,000 meters above sea level. And the base here, the Altiplano, is about 1.5, 1.6 kilometers long. This is a very interesting volcano because throughout its volcanic history, it has been exclusively effusive. There is not a single pyroclastic rock on this volcano at all, and we've been several times to look. It produces lava flows, some of these lava flows here, and domes. Some of them are a bit hard to see, but there are domes up near the summit. It produces basically effusive dacites, and the chemistry of those dacites is extremely monotonous. There's a small variation in silica content, but really it's pretty much produced the same stuff in an effusive way throughout its history. The one exception, a small, quenched inclusions about so big of andesite. They have a significance I'll come to in just a moment. So they're chemically monotonous, and they have a very distinctive phenocryst assemblage of biotite, ilmenite, plagioclase, orthopyroxene, magnetite, glass, and you can't see into there, there's also quartz and apatite. We've dated the lava flows and the domes, and we've mapped the volcanic edifice, so we get some idea as to how the volcano has grown over time. The volcano, the oldest rocks we can find, I'm sure there are older buried, but the oldest rocks we can find are 1.05 million years old, and the volcano continued to erupt until 0.25 or 250,000 years ago, and there's no evidence of volcanism since then, although there are active fumaroles at the summit. But actually there's a sulfur mine at the summit, and unlike the alpiniste we heard about earlier, you can drive to 6,000 meters, which is a lot easier climbing. And we can see this is the age of different samples, this is the cumulative volume, and we can see that although the volcano grew over this period, it grew in pulses. There's a pulse here, then a hiatus, then a pulse, then it slowed down, and then it's done nothing for the last 250 years. And so we could say the discharge is episodic, and there are periods of relatively high flux, and periods of relatively low flux, and periods of dormancy. We can use the rocks themselves, the dacites that are erupted, to say something about where the magma was when it was last erupted, where it was stored before eruption. So if we start just with the temperature, this is the temperature and the oxidation state. These are well-known reference curves for oxidation state, we can see that the magmas are erupted over a range of temperatures, 800 to 900 degrees, which is quite significant. And they have a range of oxidation states, but they're not that atypical for iron magmas. In terms of their volatiles, this is an important point. They're rather water poor. These magmas only have about 3.5% water. This is the water axis here. And modest amounts of carbon dioxide, up to about 400 ppm. Because we know the solubility of water and carbon dioxide is a function of pressure, we can deduce that this volatile content is consistent with a pressure of 100 megapascals or a kiloton. That's pretty shallow. And finally, we can use experimental metrology. We can try and recreate that mineral assemblage, those mineral compositions in the laboratory. And this is my former PhD student, Duncan Muir. And these are the stability curves of different minerals. This is temperature and pressure. We're aiming to have orthopyroxene and biotite, and that's that little skinny volume there, which again is giving us a pressure of about 100 megapascals, although there's some slop in that value. So what the daysites tell us is that these magmas were last stored, they last equilibrated at shallow level beneath the volcano. So geophysics says there's something very, very deep. The metrology tells us that the magmas, at least just before eruption, were stored at shallow level. The picture that emerges here is that this system at shallow level was formed by repeated incursions of dacite magmas into a shallow reservoir. There are heating and cooling cycles. Those are recorded in the temperatures of eruption, but also in the breakdown of some minerals. The dacite is rather water poor, and that may be significant in terms of the explosivity of this volcano. Volatile saturation is at about 100 MPa, and I've mentioned before these hydrous andesites that form these little mafic enclaves or mafic inclusions. The striking thing about those is they have really, really calcium flagellates, anorthite 85% mole percent of the anorthite component. We have an image then of the magmatic system, and this is from a paper of Duncan's. This is the shallow storage region where the magma is last equilibrated. This is the APMB, that geophysically anomalous deep body, and we infer that magmas that erupted or were generated here ascended, equilibrated briefly before eruption up here, and then emerged onto the surface. So we're invoking a connection between the shallow system and the APMB. This is the distribution of earthquakes today. Actually, we don't know the distribution of earthquakes 250,000 years ago. What's in the APMB? Well, this plot on the right shows two different ways of working out what's in the APMB. The first way, this is the top plot here, is to say the conductivity of the APMB as measured by magnetotelluric surveys is 1 cm, and we've then made, this is made measurements of the electrical conductivity of andesites with different amounts of water, andesites similar in composition to these little mafic inclusions, to see how much of that andesite we would need, what its water content would be to match the conductivity of the APMB. And in fact we find that we need a melt fraction of about 10% and a water content of about 9%. So we need a very, very wet andesite to match the electrical conductivity. And I should say that we can't do it with any other melts. They're less conductive, we need an awful lot more, and that doesn't really fit with the seismic wave velocities. There's another way we can assess what's in that APMB. I've mentioned we have these little blobs of andesite, and they have a very distinctive mineral assemblage, including very, very calcic plagioclase. And in the laboratory, we've tried to reproduce that very calcic plagioclase, and in fact the rest of the mineral assemblage. And we find here are the experiments, with the green symbols. To get 85, we need 9% water. So we actually agree that what resides in this deep crustal system is an andesitic melt with 9 weight% water. And that has a lot of implications for the amount of volatiles that will be discharged as this body evolves. And just to give you an idea, the total amount of water dissolved in the melt in the altiplano pulmonar body is equivalent to Lake Superior. So it's an entire underground, mid-crustal Great Lake. I'm not going to dwell on this slide, other than to say that it's not just andesite down there. The andesite is at 980 degrees, it contains a lot of water, and it actually melts the crust above it. And we know it melts the crust above it, so imagine, that's the one. It's hot here, this is the older crust, this depth is more like 15 kilometers. There's melting that takes place of the crust here, and we know that that's taking place because if we look at the strontium isotopes, we have dacites, these are the Uruncu mangas here, we have dacites, but they're very, very radiogenic in terms of their strontium. So that tells us that this region is a place not only where magmas are crystallizing, but where they're also melting the crust. So we are fueling this region with basalt from the mantle that differentiates to produce very hydrous andesites that supply heat and melt the crust. And here are just some thermal models from the old paper of Annen. I won't go into the details, but the point is that in the deep crust, because you're putting heat into a relatively insulated environment, you differentiate by crystallization, also by melting the crust. Okay, there's the, here are various geophysical images. Let's not go through the details, but the point is, I think this is probably the best geophysically imaged deep crustal magmatic system anywhere in the world. We have, this is ambient noise tomography, this is magnetotellurics, this is geodesy, there's a big region of uplift and the surrounding region of subsidence around Uruncu. We've done a gravity survey, these are low density bodies, that's Uruncu here, and all of them show some sort of a connection from deep up to Uruncu. It's less clear, there's less resolution in the ambient noise tomography. The gravity, obviously a rather non-unique technique, but we can see low density fingers extending from a depth of about 15 kilometers up under the volcano. We're getting images of this system, the system that connects the APMB to the shallow level and ultimately to the volcano itself. And there are a number of interesting things we can do with that configuration. If we go back to the geological map, we see that the youngest magmas, shown in the pale colour, are close to the summit of the volcano, and they're all rather short flows. And the older lavas are around the periphery of the volcano, and they're much longer flows. They come from the same vector, but they flow further. The other thing we notice is that this is Uruncu, this is Sonicera, this is the Altiplano. These are just two dormant volcanoes. These are the volcanoes of the Altiplano. There's Uruncu, Sonicera would be there. These are a bunch of others. Just take these off Google Maps. They have an average height of 1.3 plus or minus 0.4 kilometers above the Altiplano. Some of them have been decapitated by erosion. Uruncu's a little bit damaged at the top. By and large, all these volcanoes are the same height. And that's rather interesting if we think about the very simple system where we have buoyant magma deep in the crust, and we have denser crust lying above the buoyant magma. We would expect in a system where there is a connection that there'll be some relationship between the depth, the composition and the density of the magma and the height of the volcano. So we might imagine that the height of the volcano is controlled by that depth, by what's in the magma chamber, We're in a fortunate position because we don't have to speculate about the water content and the temperature and the composition. We have a complete set of experiments that we can use to turn magma composition and crystal content into density. We can actually calculate the density all the way up. We have a less good constraint on the density of the crust. This is a regionally average density variation in depth. And so we can actually, rather than use this very crude method, we can actually integrate the density difference all the way across the length. And we can calculate the height of the volcano, and different ways produce different answers, but they're always about 1.6 kilometers. So what we think is that this volcano continues to grow to a height that matches that density contrast beneath what's at the top of the APMB and the crust around. And what that opens up is the possibility that if we disturb Uturuncu, if we, for example, destroy the edifice, it will over time try to reconstruct that edifice. And it leads to an idea of top-down volcanism, where actually the magmatic system may be controlled by what happens at the surface. And one interesting possibility is that this change in output rate here, around about 600,000 years ago, might correspond to particularly intense glaciations in the region. You can sort of see this is the oxygen isotope curve. I won't go into detail as to why we see a change in the intensity of glaciations around about 600,000 or 700,000 years ago. But one possibility is that this is a response to partial destruction of the edifice and then the renewed growth. Okay, let's now move to a different volcanic system to try and understand what does all this look like, or what does a transcrustal magmatic mush actually look like if we got our hands on a piece. I've just shown you geophysical imaging. Well, the best place to go for samples of transcrustal magmatic mushes is the Lesser Antilles. Lesser Antilles is a chain of volcanoes. This is in the Western Atlantic, is South America. This would be Florida up here, North America. And there's a chain of volcanoes that correspond to westwards subduction of the Atlantic beneath the Caribbean plate. And these volcanoes are well known for their crustal zeniths, plutonic zeniths. And I've now been to every single one of those islands. It's been very hard work. But we've collected more than 1,000 crustal zeniths from all along the arc. Some of them, as you can see here, are really, really very large. Many are rather small. It's the biggest collection of crustal plutonic zeniths of any volcanic arc in the world. And I'm very keen to share that collection and to collaborate with anyone who's interested. The key thing about these samples is they are very, very rich. All that blackening on there is amphibole. The volcanic rocks of the Lesser Antilles never contain any amphibole at all, with a few exceptions. And yet the samples of mush, partially molten rock, are abundant in amphibole. These are rather nice. This is a QuemScan image from a master student of mine, and we can see pale blue plagioclase, yellow olivine, green pyroxene, so that's a troctonite or a gabbro, and then this browny red colour here is hornblende, and we see the way in which hornblende imprints itself on top of an original anhydrous mineralogy. And I'll show you just 4 more samples here. In each case, we can see these are big plates of hornblende. These are the plagioclases, olivines, and pyroxenes. This is from St. Kitts. This one's from Beckway. We can see rather interstitial amphibole here, filling the gaps between the crystals. This is also from Beckway. We can see these huge poikilocrysts of amphibole that are overprinted on an earlier anhydrous mineral assemblage. And then here is Grenada. That's a rather idioticized olivine and pyroxenes and plagioclase. One of the things about transcrustal magmatic mushes is we would expect them not to be static, but expect melts to percolate up through the crystalline framework, modifying the mineralogy as they go. And those melts, as I've shown, are very, very water-rich in the case of the Andes, and the product of that reaction is amphiboles, so anhydrous minerals plus hydrous melts will give us amphibole. What pressure is all that's happening at? Well, I have a postdoc, Luca Taberna, who is developing barometers. The way these barometers work, this is not an empirical barometer. What we're actually doing is we're taking the internally consistent thermodynamic data set, that you probably know known as Thermocal, from Holland and Powell. We have a series of reactions. We select appropriate reactions for the mineral assemblages we see, and then we look for the intersection of those reactions in ET space. Now, what we've done is, rather than use all of the thermodynamic parameters from the Holland and Powell data set, which are optimized for all of the composition space, we've focused on just those minerals that we get in these assemblages. And what we've done is we've recalibrated Holland and Powell for the specific set of reactions and mineral assemblages that occur in the Lesser Antilles cumulus. And I won't go through this slide in detail, but what we've done is we've taken all of the experimental literature where we have these mineral assemblages, in this particular case, assemblages that contain olivine, clinopyroxene, and plagioclase, or olivine, clinopyroxene, plagioclase, and spinel. And these are all the experiments out there. We've made quite a lot of experiments of our own. We've recalibrated and we've refined the activity composition relationships. We won't go into details on this. I just want you to be reassured that this is not an empirical approach. We're trying to actually develop a robust thermodynamic approach. Here's one example from Grenada. What we've done is we've found patches of this rock where olivine, clinopyroxene, and spinel are in contact. There's a lot of amphibole in here, but we've found little islands where that's olivine, clinopyroxene, and plagioclase, olivine, spinel, clinopyroxene, and plagioclase. We found places where they coexist, and we calculate the average pressure through two different barometers. We're getting around about 3 kilobars, and one of Luca, the postdoc's tasks, is to calculate the pressure for all 1,000 cumulus zenoliths and to get an image of what the crust looks like beneath the Antilles. And one of the problems here is we don't actually have a really good thermometer, which is why I was very interested in Alex Sobolev's thermometer between olivine and spinel, because that would give us an independent constraint on the temperature. Okay, so we've got geophysical images of a mush. We've got petrological samples of a mush, and they are from the right depths, 7 to 14 or 2 to 4 kilobars. I haven't determined all the pressures yet, but we're looking at sort of mid-crustal depths, much thinner crust in the Antilles, of course. Now let's focus on that process of getting from the mush to the volcano, that connection. And I'll now turn to a third field example, which is Mount St. Helens, a volcano in the western United States above the Cascades, volcanic arc, Cascades subduction zone. There's Mount St. Helens, the Nazca plate, the Juan de Fuca plate is subducting like so, and St. Helens and Mount Adams are roughly along a line perpendicular to the trench, and this is again a magnetotelluric study. This is showing resistivity now, so low resistivity here is some sort of deep melt layer. There's currently a big project to refine that. This square should move over here, sorry. But we've got a deep transcrustal magmatic mush that appears to be linked to St. Helens and Mount Adams by one or more of these columns. This is a close-up of that region there, and this is an older image where we can see the distribution of earthquakes appears to define earthquake-core regions that are often thought to represent magma storage regions, or little magma chambers, if you like, little regions where the melt functions. So let's see if we can learn something about the process of moving melt from here to erupt descent of melt from the deep crust of reservoirs to the volcano. Later, I will also point out this is undoubtedly when melt comes, we can see that very clearly, but also gas will come out. Magmatic fluids will come out. So, to get some insights into the ascent process, we're going to look at textures, the testimony of textures. These are plagioclases. The different greys are different amounts of the anorthite and albite component. These are beautifully zoned plagioclases. And I always think that zoned minerals like this are like mute witnesses to some event. They're trying to tell us what went on before they erupted. They just don't know how to tell us. We have to work out how to ask them the right questions. There's an awful lot of information locked in these zoned crystals. And I'm just going to focus on the more normal zoned crystals like this rather than the real weirdos like that. So wouldn't it be wonderful if we could interrogate an individual crystal and get it to reveal its life story, if you like, if we could ask the right kinds of questions? Mount St. Helens is a really good place to do this. Firstly, it's a very, very well-studied volcano. We have very good constraints on the phase relations, the relationship between temperature and pressure in terms of mineral stability. There are a lot more data than this. I've had several PhD students refining these phase diagrams. We've got very good constraints on mineral composition. So, for example, in terms of plagioclase, we can parameterize the composition of the plagioclase as a function of temperature and as a function of pressure. These are different pressures here. We see a variation between both temperature and pressure. And best of all, Mount St. Helens, a bit like Utarumpu, is a very, very monotonous volcano. There are some slightly more exotic rocks, particularly cumulate xenoliths at Mount St. Helens, but over its last eruptive period, it pretty much just produces dacite. So we can tend to view it as a relatively closed system, and that's really rather important. Okay, so in principle then, we could just take a parameterization of plagioclase composition in pressure temperature space. These are lines of anorthite 30, 35 and so on. That's the liquidus and that's the solidus. And we can say, right, we've got a zoned crystal. How do we move across PT space? Well, you can see straight away there's an ambiguity. Let's imagine that was our zoning. Well, we can achieve that zoning by going that way, dropping the pressure, or we can achieve our zoning by going that way, dropping the temperature. So the path is not uniquely defined. Let's imagine now that we can add another variable. You'd say, well, there's a difference in the water content between here and here, but not a difference in the water content between here and here. What if we could get the water content of the coexisting melt? Well, here are contours of water content, and then we might be able to do something a bit more with the zoning. We could say this is a drop in water content, whereas this has the same water content. We can, in principle, measure the water in a plagioclase, and we can use that to determine the magmatic water. That's not very straightforward, and there are some issues with the relatively rapid diffusion of water, so I haven't been able to do that. Let's try something else, though. Let's look at melt fraction. Let's contour that same plot for the melt fraction. These are lines of constant melt fraction, 100%, 80%, 60%, 40%, and so on. The lines of melt fraction or crystallinity are oblique to the plagioclase composition. So there's a difference then in going this way and that way in terms of how the melt fraction changes. So, if I had some means to use the plagioclase to determine the melt fraction change from one zone to the next, I would be able to distinguish between the case where the pressure drops and the case where the temperature drops. The way to get a handle on how the melt fraction changes is to measure partition coefficients. It's to measure trace elements where we know the partition coefficient. So what we've done is we've started a program of analysing trace elements and anorthite across zoned plagioclase crystals. We're going to make the assumption that the system is closed, and we're going to navigate our way through through pressure, temperature, melt fraction space. So, we make measurements with iron probe from the rim to the core. We look at the zoning in an orthite strontium bearing. We assume the system is chemically closed on the scale of an individual erosion. We assume that growth occurs at equilibrium. I'm happy to address questions on that if anyone's concerned. We'll assume that there is no diffusive re-equilibration. We'll actually demonstrate that quite convincingly in the case of strontium. These crystals, as you shall see, can't be very old. There's been very little diffusive re-equilibration. We know the partitioning of strontium and barium between plagioclase and melt as a function of composition and temperature. That's from a paper I'm drafted over. I've got a parameterization of plagioclase composition from all those many, many experiments and melt fraction. My chemically closed system is going to have the composition of the bulk magma erupted in 1980 to 86. I'm going to use plagioclase melt thermometry to get the temperature of the starting point. And then this is actually a collaboration with Oleg Melnik. What Oleg does, what Natasha do, is they then uncrystallize this crystal. They start at the end and they work out what amount of crystallization must have occurred to get from that point to that point, and then that point to that point. So they progressively uncrystallize the crystal. They maintain mass balance in the system at each increment. They recover the pressure, the temperature, the melt fraction, the proportion of the crystals that are plagioclase, and the composition of the melt in terms of strontium bearing. As well as having all those experiments, I've also analysed just over 700 melt inclusions from Mount St Helens for their water contents and trace elements. So we have a very good handle on how melt varies in this system, and the solutions here are optimized to melt, to match the melt inclusion strontium bearing. Okay, let's see what this is. That's a lot of talking. Does it actually work? So here's one crystal. It's from the 18th of May 1980. This is the rim and it's a core. This is the anorthite content. It wiggles around a bit. Here are two profiles, but it goes that's that. Then we measure the strontium, blue, and the barium. And then using Oleg's method, we recover the pressure on this scale. Big pressure drop just there, and then a lower pressure. And the temperature in red is a drop, and then it rises, and so this drop in pressure corresponds to a rise in temperature. This here is the amount of crystal, the amount of melt fraction. I should expect the magma is crystallizing, the melt fraction goes down, that's this axis here, and this is the proportion of plagioclase which starts out quite low and then becomes the dominant crystal. So we can do that for many crystals, and we can work out what that's telling us about the magma ascent process. But we need to key that into some other information, otherwise this is just idle speculation. Well, I mentioned that I analysed a lot of melt inclusions, and this is some published work. I don't have all the melting. Yesterday. These are the water content of melt inclusions from Mount St Helens. This is their silica content, and as silica goes up, that's crystallization. Water goes down. This is a process of decompression crystallization. We also took individual melt inclusions, and you can see there's a little plagioclase in there. We were able to analyse the plagioclase in the melt and do plagioclase melt thermometry. So for a subset of these inclusions, we were able to measure water and temperature. We know the solubility of water as a function of pressure, so we get a pressure-temperature path that shows as the pressure goes down, the temperature goes up. And the reason for that, of course, is these are magmas that are driven to crystallize because of decompression. The crystallization releases latent heat. The latent heat causes the temperature to rise. And this amount of heating is entirely consistent with the amount of crystallization we see. Very lowest levels, it's driven by micro-like crystallization. So, this is one record from melt inclusions. I've just described a method from plagioclase crystals. Wouldn't it be great if they agreed? I should have done this some while ago, but I was talking to Oleg about this yesterday. I said, I'm a bit worried, Oleg, that these two records don't agree. So last night I thought, well, I'll find the date, I'll plot them up, it would be embarrassing if they didn't. But if they didn't, I wouldn't plot, I wouldn't have shown them, obviously. And they agree pretty well, actually. These are four crystals, cores to rings, pressure and temperature. This is the journey that plagioclase is testifying to, in terms of pressure and temperature. This is the journey that plagioclase testifies to from core to ring, in terms of pressure and melt fraction. This is the story from the melt inclusions. You'll recognise that curve from the last plot. This is how the melt fraction varies, crystallisation this way. They're in remarkably good agreement. And it makes me quite confident that plagioclase and melt are reliable witnesses. They both saw the same event, but they saw different parts of the event. The plagioclase is recording something much deeper than the melt inclusions. The melt inclusions record this 200 MPa up to the surface. Plagioclase tells us about deeper in the system. And these pressures here are where we think the mid-crustal reservoir might be. So let's make one more check. Let's see whether the story from the crystals is commensurate with the geophysics. Let's try and complete the circle. So in the top left-hand panel there are all of the pressure points from all of the zones of all of the crystals we've looked at, turned into depth using that density. I could have changed the density, but we'll stick with this one. So it says a lot of the crystal zones were grown at shallow depth, and there are more up to about 16 kilometres. Let's look at the earthquake distribution over the last 30 years beneath Mount St Helens. There's a lot of, this scale is the same as that. That offset is because these are referenced to sea level and this is referenced to ground level. So there's a 2 kilometre offset. The earthquakes have a large peak here, shallow, and they range down to about 20 kilometres. Plagioclase goes down to 16. So the seismology and the metrology are agreeing on where magma is. And this is a very large project. I'm not part of this, but this runs out of University of Washington. And they're imaging the magmatic system. There's Mount St Helens. That says shallow magma storage zone, and this says deep magma storage zone, There's a passage between the two. This is reference to sea level again, so that's 7 or 8 kilometres, and that's the surface. I think we're starting to get metrology and geophysics reconciled. I think that's a really exciting development. Rather than speaking a different language, we're starting to agree. So the final thing I'd like to talk about, that's okay. Or shall I talk at the beginning of your... What I'll do is I'll just describe this, and then this part of the talk relates to hydrothermal ore deposits. It segues into what Oleg will be talking about after the break. And so I'll just introduce it here, and then I'll stop the talk. Here's how we think these systems work. We think we have a transcrustal magmatic mush that comprises a series of melt-rich lenses, crystal-rich lenses, and gas-rich lenses. And these accumulate over time and are inherently gravitationally unstable because we've got low-density melt and the high-density crystals. We've got low-density gas trapped in little lenses. We think that in this system, gas, melt, and crystals can move in a decoupled way, and that periodically the system experiences perhaps quite catastrophic overturn. Something I didn't say about the crystals at Mount St Helens is those rims, that journey has to have taken less than 3 years. It's based on the diffusion of trace elements. We think that the fluxes of gas, melt, and crystals out of this volcano are decoupled. They move independently of each other. And here's a lovely example from Soufriere Hills. This is the volcano when this photograph was taken. These little bright spots are fumaroles. They've been there pretty much for the last 10 years or so. They release gas, but the times of gas release are often completely, or typically, completely decoupled from the times of magma release. So this plot at the bottom here, when we see red, the volcano is erupting, green, it's dormant. Down at the bottom here is the gas flux. This is a dormant period. There's lots of gas coming out, but there's no magma. Here's another dormant period. Gas comes out, not high, but there's no magma. Sometimes they're coupled, And I think that has implications for the way in which hydrothermal ore deposits form. But that's something I'll come on to just before Oleg's talk. So I think the final slide should be... No, I'll stop. Thank you.
Вам объясню вот это, что очень раньше, скажите,
Yeah.
спасибо большое, что вы пришли.
That's right. Good question. The reason is, I think, let's see if I can find that slide. No.
Никому не говорите. Но это вообще жуть.
The reason is this, that the proportion of plagioclase crystallizing early on, deep, is really quite low. So a relatively small number of plagioclases crystallize deep, and rarely do we have melt inclusions right in the cores of the crystals. So the melt inclusions tend to occur in these sieve zones around the outside of the crystals. So cores tend to be a small proportion of the crystallizing assemblage, so that reduces the chance of getting an inclusion. But inclusions are very rarely, you can see here, you very rarely have inclusions in here. Inclusions are often in this crystal. They tend to occur just there, and then around here. This rapid decompression right here seems to correlate with burst of melt inclusion trapping. So I just don't think we have any.
I would suggest another.
Yeah.
Maybe 2.5 kilobars. It's an upper level of pressure which can hold inclusion in such weak metal like that.
Well, that's actually a certain possibility. There's one thing I'd say about that. We do have a small number of melt inclusions. I found 5 that have really high carbon dioxide contents. Now, one could argue that those are artifacts. I've reanalyzed them. They have high CO2 contents. They suggest pressures of more than 4 or 5 kilograms. I'm not absolutely confident that I trust those melt inclusions. So you may be right. Plagioclase may be a rather poor container. I have looked at pyroxenes, and I don't find any deep melt inclusions. Amphiboles nearly have always leaked. There are no olivines. So it's a good point. Either melts weren't getting trapped, or even if they were trapped, they just don't survive.
Maybe both.
Or maybe both, yeah.
Yes, John,
Yeah.
you showed nice crystals of amphibole with numerous inclusions.
Yeah.
And interpret it like percolation of the melt. Can you explain the physical state of the host rock? What was the temperature approximately? Why there are no beads which...
Yeah, that's a very good question. So you're referring to those images. I don't know is the answer. So a very simplistic answer would be to say I have an interlocking network of crystals. I have some interstitial melt. This melt is moving out. A new one is moving in. It's reacting. It's producing amphibole, and then it leaves.
It might be the metasomatic process.
Oh, it is a metasomatic, absolutely. One of the things I should say, and this is a sort of a paradox that has emerged in recent years, is if you look at many volcanic islets, their geochemistry says amphibole fractionation, and yet you look at their phenocryst contents, they're on the amphibole, and the Antilles is a really good example. So I suspect that all of the melts that eventually leave out the top of this crustal column have somehow experienced some modification by these percolative processes and have precipitated amphibole on the way, even though they no longer saturate with amphibole on erosion. There are lots of questions like the one you've just asked that I think are relevant here. What is the actual This is a percolative reactive flow. What happens to trace elements as you move through here? What's the stoichiometry of the reactions? Dissolution, reprecipitation. We see some really weird stuff in the trace elements in these rocks, but that's a whole, I don't really understand those. I think this is a metasomatic percolative process, a bit like you get in a metamorphic rock, as you pass a fluid through a porous medium.
Jon, I was surprised very much when you told that geophysical data showed that practically there are no liquid magma chamber, for only mesh, or mesh, how you pronounce it. And for instance, in polar Siberia, hundreds of dikes. And these dikes consist of olivine crystals and ground mass, just quenched ground mass.
Yeah.
So it means, but we can propose that other crystals dropped or some disappear. Yeah, but olivine here, so the most dense phase.
Yeah.
So it means that must be big amount of melt. Yes.
Okay, I see what you're saying.
Uh-huh.
I think we're talking at cross purposes. What I envisage here is this region here has pockets of, the average melt content is, let's say, 20%. In places, the melt is 100%, and in places it's 0. The average, geophysicists are just telling us about the average, across the average to melt. I would anticipate that in here, there are some lenses. Imagine building this from a series of sills. The sill that arrived last week is 100% liquid.
Yes.
Now, if that can find a way to the surface, if a crack can propagate, it can travel up, crystallizing very little on the way, and it looks like a dike with sparse finger crystals.
Yes.
Another part of the system, say here, was injected, it solidified, it got reheated, cooled, reheated, cooled. It spends nearly all of its lifetime, maybe several million years, in a near solid state. And I think the important thing is that if we were to zoom in at any point into one of these mush zones, we could access a region that was very, very liquid, or very, very solid, or somewhere in between.
Yeah.
So I think what you say is not inconsistent with this. What I was saying about geophysics is that if we want to find bodies of magma that are equivalent to the size of erupted volumes of big caldera-forming volcanoes, there aren't any. The volumes of the crust that can be entirely liquid are really small. I think they're just little lenses within this mush.
Maybe in ancient time, commodity, definitely liquid, but they're of course old.
Yeah, I don't want to speculate about the Archean.
Yeah.
I'm sticking to the modern. Yes.
Modern
Yeah.
material, yes. Thank you.
Okay.
On next slide.
No more questions? Then thank you very much.
Thank you very much.
The next lecture is by Professor Pushirovsky of the University. What Mark concluded, the key for magma evolution and the state possibilities
Иди сюда. Сюда.
Seems I have 15 minutes less than I expected, but it's exactly, it's just for convenient feelings. How much time I have? Okay. Okay. Let's start. Yeah. And this is famous lyrics of Janta Guya, Indian scientist, about inclusions. And main idea is that you need to love inclusions, and after that, inclusions open secrets. And what are inclusions? I will speak about melt inclusions mainly, and small part of the talk will be about fluid inclusions. And primary melt inclusions are portions of the melt entrapped and preserved for by growing crystals during magmatic crystallization. And we can see as olivine crystal entrapping inclusions, and some small channels are remains to the open space. And after some time, this channel will be closed and inclusion will be preserved. And here is very good shaped inclusions, full glacier inclusions from Ключевское volcano. And I will speak about volatiles because we have a new project with Oleg Melnik about modeling of porphyry system deposits. And for understanding of volatiles, there are several main papers, and first pioneer is Alex Sobolev, who measured water and melt inclusion first and shown that very high concentration of water in island arc melts. Leonid Danishevsky and Paul Wallace, who making reviews about volatiles in island arc magmas. And some pictures will be from my textbook. This book in textbook in Russian, but translation to English in the progress. I will compare inclusions with cans. You know, cans, you preserve some food usually, and if you have transparent walls of cans, you can see what inside. Sometimes we use tins or tin cans, and we need to open to look inside too. And melt inclusions is sometimes similar cans. And there is a classic picture from Marie-Lucie Frisotti review paper, and it show behavior of melt inclusion after entrapment. First, it's rounded shape, and full, it's just melt. If cooling will be fast, we have glassy melt inclusion with small shrinkage bubble. And if cooling will be slower, we have some crystallization host mineral on the walls and some daughter minerals, and shrinkage bubble will be larger. I will show several photos which not agree with this scheme. Usually first shape of inclusion very rounded ellipsoids in form, and then we can see some facets. It's a crystallization of host mineral on the wall on the inclusion, but no bubble here. Okay, here we can see daughter mineral and large amount of crystallization of host mineral. It's all inclusions in olivine. Large amount of olivine on the walls, but no shrinkage bubble. It's a backscattering image, but no shrinkage. It was not shrinkage bubble in this inclusion. Here is partially crystallized melt inclusion, glass, Kleiner pyroxene, in it's this inclusion in olivine, and no large shrinkage bubble. We have only small one. And this is from Apachon-Chislava flow. This inclusion was heated and quenched, and water was measured. It's 2% of water. And here is melt inclusion from olivolites, Kamchatka olivolites, of course. 3.2% of water, amphibole as a daughter phase, but no large shrinkage bubble. We have some bubbles on several bubbles on near the walls. That means that it's late degazing of this melt. And it's full crystallized inclusions from Gully Massive, and a lot of volatiles inside, but no significant shrinkage bubble. It means that bubble inside inclusions does not contain, not only contain from volatile contents, but depends from volatile contents, but also depends from kinetic of inclusion crystallization. And next pictures will show some heterogeneous inclusions, and it's from Marie-Lucie Frisotti paper, and we can see a lot of bubbles inside, but around its shape. It means that no crystallization in this inclusion, but a lot of bubble. It's a heterogeneous crystallization. It was melting fluid were entrapped inside this inclusion, and this melting inclusion from Talbachi corruption, and we have the same rounded shape. It's no significant crystallization and huge bubble inside. There is specially crystallized inclusion with huge bubble, and this picture very clear. It's not possibility to make produce so huge bubble from from this small amount of melt. And here it's not a bubble but plagiar class inside inclusion, and it's entrapped crystal to inclusion before crystallization. It's not a daughter mineral, it's mineral which was involved to inclusion with melt. And these two slides show that we can recognize fluid which was before entrapment, and it produce heterogeneous inclusions, and fluid which was inside, was in shrinking bubble inside inclusion. I will show one story, another other two slides more. And sometimes we have inclusions which not connected to medium of crystallization. It looks like tin, which shown on this animation. What will be inside this tin? Actually, I don't know. It may be lava, it may be some air, it may be some oil from this tin. Yeah? And there are some heterogeneous inclusions. Here is large spinel and melt which was trapped into olivine. Here the same, but with crystallization of Kleine pyroxene on the entrapment spinel crystals. And here is Kleine pyroxene inclusions. It's solid inclusion, but with meniscus of melt. We have a lot of variants of entrapment in magmatic inclusions and minerals, and we need to be careful with investigation. And here is a more complicated case. We had solid inclusion of Kleine pyroxene in olivine, maybe with meniscus of melt, but a very small amount. And then after natural heating, it was melted and produced some melt and even shrinkage gas bubbles. If heating will be more intensive, it will look like absolutely a good melt inclusion. Okay, some inclusions looks like rusted in cans. Yeah, Sometimes I'm not sure that it's possible to extract any useful information. I shown several samples, several examples from my textbook. It's we can discuss it in other lectures. Okay, now I will show a fresh sample from Talbachik 2012-2013 eruption. It was it was a very unusual eruption, and we had opportunity to get samples directly from the lava. And here is olivine crystals with melt inclusions. We can see that it looks like cans. It's preserved a lot of melt inclusions. And some of inclusions without any bevel and rounded shape. And some of inclusions the same shape contains some bubbles. This eruption had volume around 1 kilometer, cubic kilometer, and had two centers. It's Minyailov vent and Nabokov vent. And we were during Nabokov vent activity. And these are samples. It was difficult to catch sometimes these bombs. And we choose a method for best quenched samples. We collect small pieces, maybe 1 or 2 millimeter from our dress. Not such large bombs. We got large bombs too, but we investigated melt inclusions in small pieces of quenched ash. It's a place of sampling of one of that. Yeah, it's a lot of pyroclastic, a lot of bombs, but we collect very small pieces, less than 2 millimeters, for best quenching, because there is a paper about volatile loss during cooling. And this is a petrography of the samples. It's quite porous. Porosity is near 40%. And we had good olivine crystals with good inclusions. I have known that some inclusions without bubble and some inclusions with bubble. And I suppose that it's this bubble, it's not during crystallization, it's not a shrinkage bubble, it's entrapment fluid from outside. Because this melt was degassed very active during olivine crystallization. This is just lava flow, and we are on the top of this lava flow and lava river beneath us, and you can see a lot of vapor or gas from this lava flow. Okay. Here is lava front with lava very slow lava streams, and we tried to add volatiles to this lava stream, but it's not so easy. And I will discuss another sample. I will compare first sample from the vent and second sample which collected inside lava front in the liquid state too. And just wait, it will be quite hot. Where is it? Okay. Oh, it's sampling now. It's sample PK137. Okay, what's the difference? Much less porosity. It's near 8 to 10% of porosity. And there are excellent crystals of olivine with good melt inclusions. And we have different shape, show that some crystallization in the wall, but also we have some inclusions with bubble and some inclusions without bubble. But I'm sure that this bubble is shrinkage bubble. Shrinkage bubble is during crystallization of olivine to the wall. Okay, we can compare volatile content in sample from the vent and sample from the lava front. First, it's vent. We have content in inclusion with volatile content inclusion is in bubble higher than the same without bubble. I think it's clear show that this bubble doesn't content to degassing inside inclusion. It's degassing before entrapment. And if we analyze set of inclusions from this ash near the vent, we can see clear degassing path which reflects uprising of magma from 5 or 6 kilometers depth to the surface. It's clear, very good degassing path. And if we analyze lava from lava front in liquid state, it's not full solidified, it was collected in liquid state. We can see that inclusions without bubble contain the same amount of the CO2 and much less water. I think that it's due to water loss from inclusion during 2 or 3 days of lava flow stream. It's time to transportation of this olivine crystal from lava vent to the lava front. And another inclusion with shrinkage bubble contain both less water and CO2. And it's a common idea, it's not my idea, that CO2 redistributed to shrinkage bubble very well. Okay, it's about main volatiles, H2O and CO2. And major components are the same. Major components very close to bulk lava composition and very good correlates each other and fractionation in the during ascent and during lava flow. And ground mass glasses are more fractionated. It's absolutely good example for student teaching. And we can see that composition of the magma very unusual. It's high potassium. It's shishanitic in composition, and it contains quite high titanium and content up to 1.2 of phosphorus oxide. And what else? Phosphorus is lowest. Yeah, very high. It's subalkaline magma, shishanitic magma. And also very high contents of sulfur. Sulfur and chlorine. It's in this melt, sulfur is up to 0.2, 0.3, and chlorine is up to 0.1. Okay, and we just saw that it was very active degassing during this eruption, and very high initial volatile content. It's very high water, very high sulfur, chlorine. Where are these volatiles after degassing? Some of these volatiles Okay, and another point that Shoshonites are very common source for porphyry deposits. There is a good review of porphyry copper deposits of USGS, and Shoshonites and similar lavas, similar magmas are very common source in all large porphyry copper deposits. And John Blandy has idea and just told about it that porphyry copper deposits are during some degassing of magma in volcanic arc. Some volatiles we can see just on the surface of the lava flow. It's a fresh lava flow, and we can see on the surface, on the crust of the lava flow, it's not fully solidified, but we can see some sulfates, arsenates, and more complex minerals. It's easiest way to go to Mindat, it's mineralogical site, and to see how much minerals discovered in Talbachik. It's discovered more than 50 new minerals and described near 200 minerals. And it's not full list, it's just beginning of the list. And if we can see names of the minerals, okay, it's Russian names, of course, but more interesting to look to the formulas. Sulfate vanadate with water of thallium, yeah? Arsenate, sulfate of copper. Some of these minerals was discovered by Igor Pekov, who is my friend and very good scientist. Okay, sulfate of copper, potassium and sodium. Molybdate, sulfate of copper. It's a product of hot fluid which enriched in sulfate components, which just degassed from this magma. Okay, it's another another sample. Okay, can we see a copper enrichment in this fluid? Yes, we can. We can see in Talbachik, and this plot from Maxim Partadin paper in the same volume of GVGR, and we can see that some rocks are enriched factor by 1 order enriched in the copper comparing the lava. And the same in just submitted paper of my student Vesta Davidova. And there is the same in Безымянный volcano. Some rocks, mafic enclaves or xenoliths, are enriched in copper factor 10. And if we look to map, there is a Talbachik eruption and Talbachik volcano. Here is Безымянный volcano. It's one line, one zone. And I think that beneath Безымянный volcano, there is a possibility that beneath Безымянный volcano there is the same magma like Talbachik. Okay, and it's a good reason to investigate Безымянный volcano and Talbachik volcano together, because both volcanoes have similar fluid and similar possibility to form porphyry copper deposits. And this is a last scheme for Безымянный volcano from Davidova et al. Submitted paper. And we suppose that 2 magmatic chambers beneath Безымянный volcano, one with more mafic magma, one with more felsic magma, and channel between these magmatic chambers. And the most convenient place for ore deposit formation is between these two channels, because here we can expect degazing from low magmatic chamber and degazing during ascent more felsic magma. And source of ore minerals will be shoshonetic magma beneath. And how to check it? We can investigate xenoliths, which xenoliths in the andesite lava of Безымянной. And we investigated it and found that a lot of anhydrite in the xenoliths. It means that there is sulfate fluid in this system. And these xenoliths are enriched in copper and other ore elements. Okay, and instead conclusion, I will say that this project just started, and we hope that it will be very productive. And we can see that melt inclusions are possible key for understanding of degazing and ore potential of magmatic systems. And a very unusual shoshonitic magma on Talbachik volcano and possibly Безымянной. And this magmas very enriched in phosphorus, sulfur, as well as arsenates, chlorine, and other useful elements for ore forming. And Talbachik and Безымянной now are excellent natural laboratories for investigation of ore forming system and clear connected to some examples of porphyry, copper porphyry systems. And after break, Oleg Melnik will show some approach to solving of modeling problem. Yeah.
Thank you very much. You put us even before the shadow. Please, question.
So you've talked about the fluid regime and about that it was synthetic, but what is the mechanism of wearing copper into this fluid and into ore?
It's a good question. I think not a unique mechanism for this mobilization of copper. Just yesterday or before yesterday we discussed different ways for copper mobilizing, remobilizing and so on. It's quite complex question. It's a lot of ways. Yeah.
Another question, please.
I wonder, because you have a lot of phosphorus in your magma, that is very puzzling because the data of, I think, Wellman, I don't remember exactly the name, and also our experimental data show that must not be such high concentration of P2O5. So I also had some example which higher than solubility. So I believe maybe these nanocrystals of apatite may be presented in this melt. Because how to explain that? Or just water, but water does not influence very much on the solubility of water.
Yeah, it's very interesting. It's some topic for further investigation, and you see, it's not only phosphorus; it's all oxygen acids. Yeah, very high, and maybe because oxidation state very high, if you have alkaline, subalkaline magmas with high oxidation state, it may be different from your case, because usually oxidation state in common alkaline massive not so high. Yeah, it's interesting. For me, it's interesting too. We discussed it with Igor Pekov, and yeah.
Probably it is not very strange in this particular lava because it's very rich in potassium.
Not enough. 3%. No.
That's, if you take potassium phosphorus ratio, it's similar to what we expect from the metal. And also, that is quite raw silica. And also,
How much?
It's undersaturated anyway. Yeah, it's no. This one it's 53, 54.
Yeah, there is 52, 53. No,
But it's undersaturated. You too.
There's solubility.
Ah.
Yeah, because
I-
we investigated the influence of potassium with Krigman. That publication exists. Yeah.
I cannot find, but yeah, there is.
1.2.
It's a magnesium number. It's not a silica. Yeah, and
phosphorus,
yeah.
It's a little bit high. Yeah.
I think one volatile helps other volatile to dissolve. Yeah, it's because we have complex fluid. Yeah. John?
More questions? Yes, please.
Just going back to your question, the strange thing about those copper-bearing minerals is they're all oxidized. All
Yeah.
the copper are all sulfides. And yet all of those funky copper arsenates and so on, those are all oxidized. Do you ever see sulfides?
Dima Kamenetsky showed me a lot of sulfide inclusions in the Talbachik magmas, and I saw it. And I think that porphyry copper deposit has several stages. First, it's maybe sulfides, then mobilization in sulfate form, and then precipitation and ore deposit forming in sulfide again. Yeah? And these minerals are only on the fresh lava, on the surface. It's from vapor. It's not saved in ore deposits. It dissolved.
So why do you think that those gases are very oxidized? Porphyry copper systems are reduced. How do you envisage reducing the oxygen?
A lot of porphyry system have azonium, yeah, and a lot of fluid inclusions studied in high temperature zone and sulfide zone and prepelletization zone, and usually it's quite oxidized mineral. It's sulfates and very rare sulfides. Migration will be in the oxygen acid form. And if you have sulfide, it's not dissolving by fluid. It will be on the place.
Just to comment to that, it would be interesting to look at copper isotopes because they might be sensitive and they may keep some record about the oxidation reduction.
Yeah. Yeah, it's interesting, actually.
More questions? Yes, please.
What's the reason for so high concentration of copper in the volcanic system in Australia? Are those concentrations resulted from magma fractionation or maybe intrinsic to magma source or any contamination?
I think it's migration of fluid which degassed from magma, and sulfates are from fluid, which was And copper migrates with fluid. It's redistributed. We cannot explain it by fractionation. It's one order of magnitude in neighbor rocks. I think it's migration with fluid. I can't explain it but by fractionation.
Объяви перерыв. Перерыв объяви. 20 minutes. 20 minutes. 20 minutes. 20 minutes. Чай попьем. Возьми мою.
Ты вообще тоже хотел проект денег? Вообще. Ну какой грант? Просто карт, договор на карту, на ГТП. Какие там деньги? Нам денег там покушать не хватает. Еще конференцию. Нам ладно. Ну, это экскурсия. Самое приятное, что там еще пара романских появилась. Да, что же?
Вы с того будете показывать. Мы сначала с Бланди здесь.
Не, ну конференция в июне, ты не помнишь. За неделю можно написать.